You are watching DHTV from California State University, Dominguez Hills.
Hi, I'm Dr. Pamela Kreiser, and welcome back to NCR 507, which is Research Design and Interpretation. Now today we're going to be looking at the one-way analysis of variance. And this is a test that we can use in our research where we can compare multiple mean scores. As we look at this model, it's important to understand it in the context of other models that we've looked at in this class. So let's take a look at the chart that we use as a guide for when to use this kind of test. Now, as we can see on the chart, this chart is about the 6 different models that we use in this particular class. And so as we look at it, we notice a couple things. One is that most of these models involve one independent variable and one dependent variable. So we see the independent variable here, and we see the dependent variable here. And so as we look at it, we're talking about this test right here, which is the ANOVA, the one-way analysis of variance. And what does that mean then? That we have one categorical variable, and then we have one continuous variable. And so we have one categorical independent variable and one continuous dependent variable. So what basically ANOVA is it allows us to compare multiple mean scores for each of the categories of the independent variable. So as we think about the t-test and the one-way ANOVA, there's a very important distinction between the two of them. The big difference for our purposes is that in a t-test, we would be comparing 2 average scores, and in ANOVA, we're going to be comparing 2 or more average scores, and that'll be possibly for maybe 3 groups, 4 groups, something like that. And so what I want you to think about is that the ANOVA model is really a bigger t-test. In other words, it allows us to make that comparison all at one time. Now this is an important thing to understand. Let's think about the objectives of ANOVA overall. As we think about the objectives, we know that we're comparing 2 or more categorical variables on one continuous dependent variable. So what does that mean? We're looking at which group the individuals are in and what scores are produced on that dependent variable. Then we take the average scores and we examine those. Now let's also think about the fact that we're looking for group independence. And so as we examine this, we'll kind of see that throughout this process of looking at the one-way ANOVA. Now one question you might have is why wouldn't you just run multiple t-tests if you're comparing scores? And the answer is for 2 reasons. One is that it's much easier to run one ANOVA and compare all of the mean scores at one time. So that's easier for you as a researcher. And then second, and certainly more importantly, is the idea that we have less error that we're prone to when we run one test as opposed to multiple tests. So we want to watch the possible increase in error if we were running multiple t-tests. And so that's a reason why we would want to run one ANOVA test and solve that all in one process. Now, as we consider, we want to understand a few basic parts of the model. We know that the dependent variable has to be continuous because we're generating average scores. We know that the independent variable is categorical because we have to have groups that we're comparing. We know that the dependent variable is normally distributed, so that's a model that we're considering, or an aspect of the model we're considering. And then the other part that we've talked about in the previous episode is the idea that we have relatively equal variance across the groups. So we know that we have essentially groups that can be compared. Now, the last thing to talk about before we get into the specifics of the ANOVA model is that we are going to have, as we have always had, the confidence level set at 95%. And what does that mean? That means that our probability value, or our p-value, is 0.05. And that means that we use 0.05 as the standard for judging significance. In other words, if our outcome on the p-value is less than 0.05, then we are considering or judging our results to be significant. So we'll see that in just a moment as we look through specifics of the design. Now let's start with a simple example, and that is to look at a research question that might be interesting to you in this kind of a class. When we think about the research question, let's say we were looking at the following question. Will ratings of mediation effectiveness differ according to the session's location? In other words, will the ratings of how people perceive mediation differ depending on where that mediation session took place? If I wanted to know that question, then I could use an ANOVA model to answer it. So let's think about what the independent variable is. The independent variable is the location. And let's say I was comparing 3 locations. So that would be that I had 3 categories in my one independent variable. The independent variable is location. And then there's 3 categories. There's private, semi-private, and public. And so if I was comparing those 3 locations, then I'd be looking at the average rating in all 3 of those. And that's what the ANOVA model essentially would allow me to do. So my dependent variable is the ratings in each of those settings, right? And then my grouping variable, the independent variable, is which location it occurred in. Now, as we think about this, we also want to identify the null. And the null is very simple here. If the null holds up, it means that location doesn't matter. And so as we think about that, we identify that the null means that there would be no difference depending on where you had the mediation session in those ratings. In other words, they would be different, but not significantly different. Now let's take a look at the data on the screen. So as we look at this screen, we can see that we have a bunch of numbers on the screen. And we see at the top here that we identify the independent variable, and that's the location. So we see that there's a number of scores in one location, then there's a second location, and then there's a third location. And so we see that this is all one independent variable, but it has 3 different options of where the location would be. So we see that indicated by the 1s, the 2s, and the 3s. Now on the other side, we see the ratings. And these are continuous data measurements, and they are for each of the different locations. So you can see on each row, there's someone who was in location number 1 and then gave that rating score. And here's someone in location number 2 and they gave that rating score. And you can see how it's laid out on the screen. Now, one thing that you might notice on the data is that you might notice that we see kind of some higher ratings, honestly, in the 3rd setting. And we see maybe some lower ratings on the 1st setting. And so as we're kind of comparing them, just looking with our eyes, we might notice that there are some possible differences here. Okay, now one thing you might be wondering about is the area of degrees of freedom. Perhaps you've heard of this idea. This is the term that researchers use to talk about how the scores can vary. That's basically all it is. And so what we know is that we can define the degrees of freedom for the analysis of variance, and we have to define the scores in 2 ways. So we have to look at the degrees of freedom between and also within. And as we go to this screen, we can see that there are 2 different formulas that are for the model that we're talking about. One is between, right here, and then one is within. Now, as we identify the degrees of freedom, we know that the formula for how the groups can vary between groups is the number of groups minus 1. So for our purposes, we had 3 locations, and we're going to subtract 1, and that means that we have 2 degrees of freedom between. Now, the second part of degrees of freedom calculation is to look at within, and that's right here. So here's within. And we know that that formula is the number of participants minus the number of groups. So that's how the scores can vary within the groups, right? So there's variation between the groups and variation within the groups. So the formula for degrees of freedom within is n minus k. And so in our example, there were 18, so we can see that right here, 18 people in our study, and where there are 3 groups or 3 locations. And so we know that we have 15 degrees of freedom within. So we have 2 results here that matter in terms of the ANOVA. Now, the first part of writing up the equation looks like this. We put these different numbers in parentheses to help us communicate the results of the ANOVA that we're conducting. And so here, we know that when we begin to write this up, we are going to report the degrees of freedom in parentheses, and we know between goes here, and then we know within goes here. And that helps us identify the degrees of freedom between and within. Now, the next part of doing the data analysis, and we can go to the screen here again, is to take a look at the data in a larger picture, and we can see all 18 of the scores here. Now, when we run the ANOVA, we are going to run it, and I give you a separate video about this on our website where you can look at the ways to run the ANOVA, and basically you'll see that that's a pretty easy process, and we're going to conduct that separately. So after I ran the ANOVA, then I would get some results. And so let's take a look at the next screen, and it will show me that. Now, the first thing that the computer will give me are these output pages with the following boxes on them. So you can see the first box is the between subjects factors. And as we look at this, we notice that there are 6 cases in each of the 3 locations. And that doesn't surprise us because we saw that in the data. And so we're looking at that. The next box we give is really, really important. So first of all, it identifies or confirms back to us that we are comparing ratings, and that's our dependent variable. And so what essentially we're doing in the ANOVA is comparing the average rating in the public setting, right here, the semi-private setting, and the private setting. And so essentially, on its most basic level, this one-way analysis of variance is a comparison between these 3 mean scores. And as we look at it collectively, we are asking the question, do any of these scores differ significantly from any other scores? And so we would look at it on the face of it, and we might say, wow, I noticed that 76.3 looks kind of different from 90.16. And so as I evaluate that, I might think to myself, there's probably a difference there, but we don't know if it's significant. And the ANOVA will tell us the answer to that. So if we go to the next screen, we can see the F ratio box. And this is also a very important box because it gives us the results of the ANOVA model. Now, the ANOVA model is significant when it says a difference exists down below in the data. Now, you might say that's kind of funny phrasing. Like, why would we say it that way? We say it that way because when we are looking at the analysis of variance, this is the box that tells us the overall model. And then the next one we'll do in a minute will show us the specifics of those comparisons. So here we have the between subject effects box. And this is really important. We see, again, the dependent variable is ratings. And so when we look at this model, there's a few numbers that we care about. So we care about this one, which is 2 and 15. And those are our degrees of freedom. Remember, we calculated those together a few moments ago. So this box actually tells us what those numbers are. We have the actual F ratio right here, which is 8.337. We have the significance of the model, which is 0.004, and then we have the eta squared, which is the effect size, 0.526. Now, the next part for us to do as researchers is to evaluate, do we have a significant model? And in fact, we do, because we see that the significance is less than 0.05. We determine this because 0.004 is smaller than 0.05. Now, if I were to take this result and put it in a write-up, then I would write it up in the following way. I would start with F, and then I would put my degrees of freedom. And then I would report the F ratio, that's right here, 8.337 with a comma. And P is less than 0.05 because I had a significant result. So that's this score. And then I'm going to put the eta squared, 0.526. I'm running out of space. Okay, you get the idea. So let's take a look at where all of these numbers come from. We see that this 2 comes from here. We see that this 15 comes from here. So these are the degrees of freedom. And then we know the very important number, which is this F ratio, is the next one reported. That's this number, that 8.337. And then here we're going to report whether it's greater than or less than 0.05. In our case, it's less than 0.05. So for the reader, they would be able to understand this model very well from looking at these numbers. They would see that the 0.05 indicates it's significant. And then my last reporting is the partial eta squared, which is indicated here. And I ran out of space, but essentially that would be 0.526. So we can see on this screen then how to properly write up the results of this F ratio box. Now the next screen is also very important. And this is where we're going to look at this separate cell comparisons. So when we look at this, we're looking at the multiple comparison box. And the one that we ran was the Tukey HSD. So that's the Tukey honestly significantly difference test. And what that means is it is going to be a test where we can compare one location versus the other. So let's take a look at this and understand what we're seeing in this box. Now, the most important part for you to note is that this is the box that we care about. And that is where we're going to look to see if we have a significance or a p-value that's less than 0.05. So if we look over to the left, we can see that public is being compared to semi-private, meaning is public significantly different from semi-private? And here we see it is greater than 0.05, so it is not a significant difference. Now next, we see public being compared to private. And when we look across, right, we can see that yes, it is a significant difference because it's less than 0.05. So here we see not just like we did in the F ratio box, indicating an overall difference in the model, but here we see the specific difference, and it was just like we talked about in the beginning of the show, is the public setting, are the ratings in the public setting significantly different from the ratings in the private setting? And we see, in fact, our model does show that they are significantly different. Now, one of the things to know about the chart that you're looking at is it will compare everything to everything else twice. And so now we're going to see semi-private compared to everything, and we don't see any differences. No differences there. And then here we see private being compared to semi-private and public. And here again we see the same result. That's that 0.03, and we see that that is in fact significant. And so just to review then, we see two significant indicators here, and they're the same result: public versus private, private versus public. And so the great part about the Tukey post-hoc comparison is that it allows us not just to know there are differences like the ANOVA model, but it specifically tells us where those differences are. Now remember, our original research question was was the following: will ratings of mediation effectiveness differ according to mediation session location? And we found one significant difference, and that was shown up in the F ratio box, and then we also saw specifically which ones. So we found that our results show that there are significantly higher scores, higher ratings for those who engage in mediation in a private setting compared to those who mediate in a public setting. And so based on our results, we can say that they are significantly different. And the reason we can do that is that we actually ran the test to make that determination. We also know that we found out that public and semi-private are not significantly different. And we also found out that semi-private and private are not significantly different. Now, this might be very interesting information to have if you had only partially private cubicles or areas available for a mediation session. You would be able to make some decisions based on the data that show that if I were debating whether a semi-private or private location, I know there isn't a significant difference between those two. Or I might say, oh, I only have a public or a semi-private setting available, and we know those aren't different. So truly, all the way public or all the way private is where the difference lies. So let's wrap up and talk about this a little bit and say that we want to think about how we would explain these results, because honestly, we can find out the numbers, but we have to figure out how to explain possible reasons why this might be occurring. So let's say I ran that study and those were my results, and I would need to explain what I think is the reason behind this situation for getting these results. And so one reason I might explain it is that when individuals are, perhaps the reason for the difference is that when individuals are in a private mediation setting, they might have fewer distractions. And so they might be able to focus on the mediation session, and this might translate into higher ratings. So that could be a reason, perhaps, why we might rate it significantly higher in a private setting. I might also talk about perceived privacy, that maybe when we're in a private setting, maybe it's not that it is less distracting, but just that I feel like it's more confidential. And so as I think about that, I might maybe tie that to why I think it's effective or not. And I could be rating it on satisfaction or effectiveness, whatever you decide your dependent variable is. And then the other thing we could talk about, of course, is the distractions on the public side. So we might be able to explain it another way and say one of the reasons that the ratings are lower in the public setting is that there are other people around, or perhaps there are too many things to look at, and even interruptions possibly. And so as we think about that, those are different explanations for why we got the results we did. Now, one thing you may have noticed in my language is I use terms like it may be because, or it could be a result of, and I use those phrases because we can't say for sure it is due to that thing. We can only say that this is a possible reason why we might have found the results that we did. So today we've been able to identify that important model, the one-way analysis of variance. We observed that it has a categorical independent variable, and usually I like to use it when I have 3 or 4 or 5 categories in my one independent variable. And then we also noted that it has a continuous dependent variable, and when we talk about this, we know that it is a continuous variable where we can create meaningful averages. And so when we look at the average comparison between one group versus another, we can see actually what the ANOVA model is built to tell us. Of course, we notice that the F-ratio box gives us an indication of the overall model. So do we see significant results somewhere in this statistical analysis? And we found in our results we did. And then when we go to the Tukey post-hoc comparisons, we can actually take a look at where those differences lie specifically. And then ultimately, as we write it up mathematically, like I showed, and then even in writing, as we just talked about, we can explain these results to try to help other people learn things from what we've conducted in terms of our research. Now, you might find this to be actually a useful model in your program evaluation. So think about using it there. And either way, you know now the one-way analysis of variance. So that actually concludes our show today. And I'd like to thank you for joining us. And remember, I hope that your day is not just different, but significantly different.